All right. So everybody online can see my screen this time. Sorry about forgetting to share that last time. Um, at least we weren't doing a whole bunch of coding examples yet, but we're going to start that today, hopefully. Um, and I'm also recording. I did remember to record last time. You just got to watch me talk for an hour and 20 minutes. All right. Um, just so everybody knows, maybe you already saw it in in our prayers. I have back surgery every Friday for the next 3 weeks, so I might be loopy over the weekend. If you email me and get um, a weird response, that's probably the reason why. Um, I had 6 back surgeries last year, and to allow me to golf again, and then I ripped the titanium out golfing. So those didn't work. so now they're making a more permanent fix that won't let me golf, but nothing major, just a thing. Okay. So again, I'll confirm online. Everybody can see my screen. It's being shared.
Yeah.
All right, good. And I am already recording. Just confirming that. Yep, I am. Okay. So, just a quick review from last time, and then let's jump into variables. And the plan is to have your first programming assignment over the weekend. Um, so, if you remember from last class, we talked about kind of looking at programming languages through a couple of different lenses. Um, so, we might say there's two kinds of programming languages. So one of them deals with how variables work in the language. So we have loosely typed and we have strongly typed languages. One's not necessarily better or worse than the other one, just loosely typed languages are languages like Python and JavaScript and PHP. Whenever a brand new programming language comes out, whenever you hear about a new technology, a new coding language, very high chance that it's going to be a loosely typed language. They're a dime a dozen. They come out every 15 minutes, and they're all based on the C and C++ programming language. Strongly typed languages also tend to be compiled languages, which was our second slide or next slide here. These are languages like C, C++, Java, Swift, which is Apple's language, Objective-C. So these languages tend to be strongly typed. They tend to be fast. They tend to be compiled. They also tend not to come out every 5 minutes. Because creating a compiled programming language is substantially more complex than creating an interpreted programming language. All right, because most of the time interpreters are written in a compiled language. So through a different lens, we have two kinds of languages. We have interpreted languages, where during runtime, the lines of code we wrote get translated into something that the CPU understands. So there's kind of a little bit of a delay in there, probably nothing that we'll notice as humans, but if you're writing a video game or something like that, an interpreted language might not be the right tool for the job. Compiled languages, again, like C, C++, Java, yada, yada, yada. These use a piece of software called a compiler that we type the code out first, we run it through the compiler generates a low-level language, like assembly code, and then there's a linker that turns it into an executable. And then at that point in time, when you double-click on it or you hit run, now it's running on the CPU natively. There's no interpretation being done at real time, at runtime, rather. All right. Important piece here is one of these languages isn't necessarily better or worse than the other one. In fact, you might even say that your most flexible programming language is an interpreted language that it will exist on every single computer you touch. And that's JavaScript. Every web browser runs JavaScript, so nothing prevents you from sitting down at grandpa's computer, running Windows 95, popping open a web browser, creating a text document with some JavaScript code embedded in it and running your program inside of their web browser. So every computer already has the ability to run your programs without you installing anything. All right. So talked about a compiler, just a tool translates a high level language into a low level language. Linker, kind of that drags it across the finish line, making it something that actually runs on the computer by bringing all the libraries that it's relying on that are like part of the operating system and stuff like that into a single executable file, with the idea that you could take that file to a different computer that is running the same architecture and the same operating system, or at least backwards compatible with the same architecture and the same operating system. Double click on it and it'll run. Okay. Sometimes you've maybe seen this in Windows before, where if you're running kind of an older piece of software on a newer version of Windows, if it acts kind of funky, there's a way you can run it in compatibility mode, right? If you haven't seen that before, you right click on it and say run in compatibility mode. You could choose what operating system you want Windows to pretend to be. Windows 95, 98, XP, whatever it is. Basically go back in time as far as you need to go until that operating system natively supported whatever that executable was built on. All right, because keep in mind, every time a new operating system comes out, it's probably going to have some bells and whistles in it that the previous one didn't have. All right, and even though most operating systems, as well as most architectures, are backwards compatible with the previous one, every now and then, in order to implement a brand new feature, they might have to break an old feature to make it work in a more efficient way or a different way that might make some executables not function. So that means you would either need to port that software, recompile it at the very least for that operating system / architecture, or run it in some sort of compatibility mode, which effectively makes it interpreted, right? During runtime, it's kind of going through some sort of zig and zag to make it run on that computer. Most of the time, you're not going to notice. All right. So we kind of stopped at this slide here. So let's power through these. So there's 3 kinds of programming languages. Another lens. We have procedural languages, we have object-oriented languages, and we have functional programming languages. Now, what I'm going to do here is I'm going to just pretend like this slide doesn't say functional. Functional languages are very difficult to describe unless you have one sitting in front of you. Okay, so functional languages work by having a whole bunch of functions you call in terms of each other. Popular functional languages are languages like Lisp, Haskell, Scheme, things that you will be introduced to in this in your computer science program here, but not kind of what we're looking at right now. So we're just going to throw next to this guy languages like Lisp, Haskell, Scheme, which is a superset of Lisp, etc., etc. Store this in your head for later use. All right. So I'm not going to be testing you over anything related to functional languages or anything like that. It doesn't quite fit the puzzle that we're in right now. And those languages are just different. Not that your programming skill set won't translate to them, but they are a substantial deviation from a problem-solving perspective than the first 2 here. First 2 here, what we're really interested in here. Chances are any programming language you've heard of is either procedural or object-oriented. All right. Maybe a couple of you in here, when I mentioned it, had heard of Lisp or Haskell or Scheme. How many of you had heard of any of those languages? Okay, so Lisp is kind of a famous artificial intelligence language. Then Haskell came out, also artificial intelligence. Scheme kind of is more of a general purpose version of Lisp to do some other stuff. But let's just leave functional at that point right now. All right. So procedural languages, these tend to be monolithic in nature, where all the code exists in one file or a relatively small number of files. And as the program gets larger, the code becomes harder and harder to follow. Okay, and we're going to understand that a little bit better through an example here in a second. All right. So everybody in here at some point when you thought about becoming a programmer or something like that, you probably heard of this idea of object-oriented programming. Okay, OOP or whatever like that. Anybody know what it means for a language to be object-oriented? It kind of falls into this category of tech buzzword that nobody really knows what it means in general. The reality is it's quite simple. And let's look at it through an example. All right, so we're going to use our imagination here. Up here on this table, we're going to have a giant pile of wires. All right, we have a pile of wires laying here. Now, I tell you, this is a telephone. All right, you come over, you inspect it. There's all sorts of crap laying here. You find a little handset, you hold it up, you hear a dial tone, as if those exist anymore. You see some of the different things here. So finally, you're convinced, like, okay, well, there's a lot of details sitting there, but I'm convinced that is a telephone. Just doesn't really look like a telephone. All right. Now, do we believe you take one of these guys that there's probably a whole bunch of those wires and stuff like that all embedded inside of this pretty little case that makes it not look so scary as this pile of wires here, but still has all those same functions? True statement, right? Okay, so any of our electronics we have, same thing. This computer right here, it looks like a laptop, but inside of this, it gets quite complicated, right? Okay, so a procedural language is kind of like this telephone example we have over here, where it's a giant pile of wires, where there are both public usable things that the human being is meant to interface with, as well as things that did need to get built, but kind of get shoved under the hood, right? A procedural language, what it does is what it doesn't do is it doesn't have strong tools to shove those details under the hood. All right, they're all just laying out there in the open, along with the actual aspects of the program that the human being needs to interface with. Now, that would have been fine for a long time when, in early days of programming, when the types of problems we were solving with computers weren't as complex as the problems we're solving today. It's not that people were stupid. It's that A, computers weren't as capable. B, human beings didn't have as much experience working with them and exploring the types of problems in our daily lives we can use computers to solve, right? And then once we put those together, we just, human beings get greedy. We just keep finding more and more things. So eventually what happened is these procedural languages kind of lacked the organizational tools to allow our code to be easily managed, certainly by groups of programmers who are working together on a large project. All right. So the object-oriented telephone looks like a telephone. We believe that all of those wires are shoved inside. All right. So you can imagine that we have this box, and we're going to take all those wires, we're going to throw it in that box, and we're going to seal the top of the box up. Then we're going to poke some holes in that box, for the aspects of that telephone that we actually need to interact with. Okay. So we'll have the buttons for dialing. You'll have the whatever you're speaking into and the thing you're listening to, all that stuff. Those things will be hanging out of the box, but all the other stuff that is there, that works, that you're never going to touch again, is nicely housed inside that box. So you don't have to see it. Make sense? That is what object-oriented programming is. It's a procedural language with an additional tool that allows you to organize your stuff into little buckets. Typically in object-oriented languages, those containers, those buckets, are called classes. That's effectively the difference between a procedural language and an object-oriented language. All right, so we're going to say many of the details that a human does not need to readily interact with will be hidden away so that only the public facing features are easily accessible. Not that we still can't get to those other things, right? So even though you told me you believe that there's a bunch of complicated stuff inside of here, or there's a bunch of complicated stuff inside this laptop, with a flathead screwdriver and a hammer, we can get some stuff. We can start seeing some stuff, right? That's the difference. They're basically the same. And guess what? I'm going to make up a number, but it's pretty close to accurate. Let's just say 99.9% of modern programming languages, regardless of whether they're interpreted or compiled, whether they're procedural or object-oriented, doesn't really matter. They all have a common ancestor, and that is the C programming language. All right. And you're going to see pretty quickly here that what we're going to be writing for the first several weeks of this class is effectively C, a procedural language. And then as we start seeing that, oh, well, our programs are getting complex enough, or maybe it's just that my teacher said we have to start putting things in objects, we're going to transition into C++, which isn't even a different language. It's just C with this new Tupperware that allows you a thing called a class. It allows you to stuff your wires into it. That's the difference. Okay? Questions about that at the high level? We'll see this in reality as we roll through here. All right. So something I said at the beginning of the last group of slides, where we are kind of making sure that we kind of identify, we pigeonhole a programming language into what category it fits into, and that will allow us to kind of know how to wield the language when we're trying to select the right tool for the job. All right, because there shouldn't be a such thing as somebody who says, "Oh, well, you know, I'm good at Java, but I'm not good at C++." They're the same language. It's the same thing. But if you didn't learn how to program from the bottom up, and instead somebody just threw you into a Java tutorial, your perception is, oh, that's all I know, is how to code in Java. Okay? All these languages are the same. But there are some nuances. For instance, if you are writing a video game, in your mind, you might immediately say, okay, well, unless this game is very simple, kind of a la Angry Birds, something like that, something that's not, you know, you're not measuring your frame rate on the game Angry Birds, right? So if, you know, but in general, if you're writing a legit video game, let's say, you're probably going to instantly cut out anything interpreted, which probably instantly cuts out anything loosely typed. So now you've cut out, frankly, if you really add up all the languages that exist, 99% of the languages are thrown to the side. So now ultimately your decision is going to be, well, am I going to write this game in C, C++, Java, C#, Objective-C, or Swift if I like naming variables with emojis? True statement. That it's ridiculous what Apple did with my background's in developing programming languages. So when Apple came out with their Swift programming language, which tried to be everything to everybody, and they allowed you to actually name variables instead of like with a name like my age, you could call it with like the poop emoji. That is dumb. But they did it. They did it. Probably along the same time as they were coming out with the iPhone had the Animoji things, where you took a picture of yourself and it turned you into a cat that moved and stuff like that. I don't know. Whatever. All right. So for example, if we're looking at C, we should know that, okay, the C language, it's a high level language. So we're not talking zeros and ones. We're not talking on a one-to-one relationship with the CPU. We're speaking a high level language. This is a power tool. It's an old power tool, but it's still a good power tool. And like I said, pretty much every language you ever program in your entire career came from this guy. All right. It's a strongly typed language, which means every single time I want to remember something in it, I have to specify the kind of value I want to remember, not just what the value is, but specifically what type of value that is. All right. It's a compiled language, which typically goes with strongly typed. And it's also procedural. This guy predated the idea of object-oriented languages, although it has tools in it that allow you to kind of accomplish object-orientedness hacking through something called structs. And we'll see those. C++, basically the same thing as C, we just added a class and changed a couple of other little rules, but those are more quality of life stuff, nothing earth-shattering. All right, so let's get into variables. So we're going to start seeing code here pretty quickly. So let's talk about what variables are. Remember our slide back here, how do human beings solve problems? We remember things, we ask questions, and we use repetition. And I said 100% of programming languages have facilities for these three things. All right, well, and then that next slide was the mapping. This guy, we're remembering things is kind of our variables. So when we're coding and we have stuff we want to remember from line to line to line or in a different part of our program, these are going to be variables, and we have to play the game of the variables we're working with. All right. So you can think of us effectively using C++ in this class, but C++ and C are identical for the first while. The only difference that I'm going to be doing, because we're ultimately going to be using C++, is I'm going to be using C++'s IO libraries instead of C's IO libraries. And what I mean by that is for like printing stuff out to the screen, in C, you use a function called printf. In C++, you use a function called cout. They both print stuff to the screen. Okay, so we'll use cout inside of our C-like programs so that when we get over to the object-oriented stuff, you're not having to print stuff out a different way. Cout is written in terms of printf under the hood. So doesn't really matter. We'll just keep it more modern. All right. So variables. Because we're using a high-level, strongly typed, compiled programming language, we know that any variables we're going to be creating, we have to define the kind of value it's meant to hold. So syntax for variables is type followed by var name equals value semicolon. And actually, this part right here is optional because you could define a variable and then give it a value later on if you wanted to. But usually when you create a variable, you'll give it a default value, a starting point. All right, we'll see this in action here in a few minutes. So this is more the theory behind it. All right, so let's talk about these pieces here. What's a type? So a variable type, you can think about these as if variables are little containers, like our Tupperware containers from our example last class with tax documents and shoes or whatever example I used. I think that's what I used, right? You know, it's like that sticker you put on that guy labeling what belongs in that box, what's allowed to go into that box. Okay, so types in a programming language are going to be anything that you can create a variable of. Now, there are types built in to a programming language. So we have primitive types. These are built-in variable types that come with the language out of the box. So when you first crack open C or C++, it already has a bunch of types associated with it. We're going to talk about those in a minute. Then we have object types. We could say some of these come with the language. More and more of that is true in our more modern languages like Java and C#. They come with a zillion object types built into it. How many object types do you think come with C? Trick question. No, not an object-oriented language. All right, so but C++ comes with a couple of them, but it's they hide it inside of something called standard lib, standard library. All right, so object types, some of these come with the language, but most of these are user defined, which means we're the programmers. We're going to invent our own object types, our own variable types of type object, where we decide what kinds of values get stored, what kinds of magic tricks those objects know how to do. So we can invent an infinite number of variable types to our language. These are things that didn't come out of the box. Make sense? All right. So let's look at primitive types. We'll say in C, but I'll tell you what, with very, very, very little change, this list is applicable to C++, to Java, to C#, to Swift, to Objective-C, basically every one of our compiled languages. Every one of our strongly typed languages all share the same group of primitive types. Why? Because all came from C. All right, so our primitive types are byte, short, int, and these are all lowercase, but it keeps capitalizing them for me. Whatever. Long, char, float, double, and bool. All right. Actually in C, bool is actually an int. In C++, it's called bool. Java, it's called boolean. Actually, C++ is bool all caps. C# is bool all lowercase. Mind shattering. All right. So we'll just say, we'll even just spell it out, boolean. All right. These are trues and falses. All right. So we'll start down here. We'll say true or false. That is what a boolean value is. Don't really worry about that very much right this second. We'll be worrying about that very soon when we start asking questions and having to form Boolean expressions. Okay, but if we were to store a single Boolean value, we'd be holding a value of either true or false for whatever reason we might want to do that. Okay, let's go up to byte. A byte holds whole signed integers. A short holds whole signed integers, and int holds whole signed integers, a long holds whole signed integers, a char holds whole unsigned integers. So let's just look at these first four here. So we have four different types built into our programming languages: byte, short, int, long, and they're all capable of holding the same kind of values. What do you think the difference between these guys are? And then why do they exist? What do you think the difference is between a byte and a short? You've heard the word byte before in here. What is a byte? Yeah, 8 bits. Okay, collection of zeros and ones, 8 of those. What's the maximum size value that we could store inside of a byte? 8 ones, okay, which is 256. All right, so now, since these guys are signed, we actually only use 7 of the bits for the number, and the other bit is used for sign, positive or negative. Not as directly as you might think it is. It uses something called 2's complement to encode a value as a negative number. That's something you'll mess with in the 325 class next semester. Not something you have to worry about in here. Just know that under the hood, a byte can hold positive and negative numbers, and it just figures it out for you. All right. But the kicker with this is this is a 8-bit signed value, which can hold the values between negative 128 to positive 127, which is 256 unique values. So 8 bits can represent 256 different values. This kind of blurs that line we mentioned last time between numbers and indexing, keeping track of unique things. So a byte can hold 256 unique permutations, ranging from negative 128 to positive 127. And it magically does the encoding under the hood using something called 2's complement, which is why we have one smaller value on the negative side. That's why it goes to negative 128, but it only goes to positive 127. Okay. Again, something I'm not going to test you on, but the punchline to the reason why is we don't need a positive and a negative 0. Right? So why store it 2 different ways when we can just give ourselves one extra value to represent? 2's complement mathematically makes that happen. Where 1's complement or just sign and magnitude, where you just say, well, negative numbers have a 1 at the beginning and positive numbers have a 0 at the beginning, and now you have a positive 0 and a negative 0 for your final values. Unimportant for us in here because we're programmers, we're wielding this thing, but that's what's happening under the hood. Okay, so from our perspective, the byte primitive type, it can hold a range of whole integers between negative 128 and positive 127. A short is a 16-bit signed value, which could hold negative 32,768 to positive 32,767. And by the way, this is plus or minus 2 to the 7th power. This is plus or minus 2 to the 15th power. So if you were to do 2 to the 15th power, you get 32,768. That's where that number comes from. An int is a 32-bit signed value. And this is negative 2.1 billion to positive 2.1 billion. So that is 2 to the 31st power, 2.147483,648 billion. Anybody want to guess what a long holds? 64-bit. So this guy's a 64-bit signed value. So this is negative, I think it's 9 quintillion. Positive 9 quintillion. So that's 2 to the 63rd power. So 9.223. So that's 1,000 million, billion, trillion, quintillion. Yeah. Or is it quadrillion? That's a big number. I think it's quintillion. Okay. But it's a really big number. All right. So all 4 of these types hold whole signed integers. Why do you think we have 4 different ways of holding the same kind of values? Can we store the number 7 inside of a byte? Can we store the number 7 inside of a short? Can we store the number 7 inside of an int? 7 inside of a long? Sure. 7 fits in the range of all these, right? Why do we have so many different ways of holding a number like 7? What do you think? We answered the question, I think, last class. Keep in mind the vintage of the C programming language. Go ahead. Yeah. Yep. So we talked last class about the Y2K problem and kind of where that came from is because memory used to be really, really, really expensive. And we saw a couple examples of that. Well, C came out when memory was really, really, really expensive. So they needed to give computer programmers like us the tools we needed to be as granular with how we use memory as possible, which means if we only needed to store the number 7, we're not going to use a 64-bit value to hold the number 7. We would use a byte to hold the number 7 because that is the smallest data type the C language gives us for holding. So we have 8 bits is the minimum data type we have, minimum size data type we have for holding numbers. So we can't get any more efficient with C than to store a 7 as 8 bits. That would be 0, 0, 0, 0, 1, 1, 1. That's the 7. So a little bit inefficient, right? But still, as a programmer, we get to choose to use a byte because the value we're holding doesn't need any more than that. And now we're saving a little bit of memory. But that little bit of memory we're saving here actually used to be quite expensive. Now we don't care. Unless the only time we'll care now is when the numbers get so ridiculous that we already know enough about how to care. Okay. Chances are when you're early on, when you're programming, minus you writing an infinite loop, which just builds some number up to something crazy, it won't make any difference to you. So as a modern programmer, if you need to hold a whole signed integer, when I say signed, I mean it could hold positive and negative values. You're just going to use an int. And if int isn't big enough, you'll throw it in a long. And if long isn't big enough, then you jump over to the object-oriented side and start searching to see what's there. Java has something called big integer. C# has the same thing. Otherwise, in older languages like C, you could write your own tool for holding larger values. Because now we know how numbers work, right? All last week, we looked at converting things and we realized, hey, we learned this in 2nd grade. Now we just applied that knowledge from 2nd grade to all sorts of different bases. All right, so your default, when you're looking at some code and somebody's holding a whole number, you're going to probably see it defined as an int. Well, now we get to a char. Now notice a char is very similar to the definition of a byte short int long in that it holds whole unsigned integers, which means it cannot hold negative values. Now, when you hear a type called char, what do you guess that probably is meant to hold? Go ahead. Yeah, a character. And when a human being hears character, we're thinking about things like A, B, C, maybe a question mark or a comma, characters, right? But we've already talked about in here that computers like numbers. So we even mentioned how computers deal with characters in here. Remind me, how do computers deal with characters? We talked about 2 different character sets. Remember we had something called, go ahead. Yep. So when we were talking about using using a number to index stuff rather than do bases, rather than do math with it, we talked about ASCII as well as Unicode. ASCII is an 8-bit character set. Unicode is a 16-bit character set, which means that, and in most of our modern languages, a char is 16 bits. In C and C++, a char is 8 bits. So this is a 8-bit unsigned value. So that ranges from 0 to 255. For 256, unique characters that can be represented by an 8-bit character. Make sense? Now, technically, you could do math with that because of how it's stored. You could say, I want to add A plus D and get a number. You could force it to do that because you know, as a computer scientist, that under the hood, it's stored as a number. All right. But it's meant to represent a char. So when you've labeled a variable as being type char, you said, hey, this bucket I just invented is made for holding a char. When your program's running, whenever you use that variable, it will automatically notice that it's a char, and it will go and do the lookup for you and spit out the character that you stored in there, not its numeric representation, unless you force it to do the numeric representation. You got a couple of ways that you can kind of juice it if you want to, through there's various conversion tools for it. But in any case, when you're storing something in a char, it'll do the mapping for you. All right. So float. These are decimal point signed numbers. And so is a double. So a float is 16 bits before the decimal point. Yeah, this is true for C. Things get a little wonky in here when you get to more of our modern languages where it jumps bigger than this. So for instance, in Java, a char is a 16-bit unsigned value. So 0 to 65,535, because it's representing Unicode. But the types are the same. We got an announcement or something, or go ahead.
Study sessions going on Monday nights from 4:30 to 6. When you can, when you have to. We have a lot of fun. We don't just study, talk about things. Always do things. I got a couple other events planned for this semester and next that I'll announce relatively soon. So yeah, look out for those. I'm Simeon, president of Hackathon Club. Our first hackathon is on September 30th, I think, right? That's right. It's in a couple of weeks. There's a message on Slack about it. Trying to go out next week for it. Real short, 5 to 9 p.m. that night.
Yeah, so this starts the hackathons actually give you quite a bit of experience. It's a really cool thing to see what you will be capable of doing, since most of you are going to be going there with very little to no experience, right? So you're basically going to be sitting there watching other people, but you'll learn the process and you'll start seeing how these things start coming together. So the hackathons are definitely for you as well. It's not something you're just going to come and sit there and twiddle your thumbs. As long as you get involved, you'll watch it. You'll be part of the problem solving, even if you're not the one necessarily writing the code heavily. But they'll give you a part of the project to work on once, because you'll wrap your mind around it pretty quickly. All right. Anything else? Any questions for them? And they make their announcements usually over Slack, so make sure you're on the Slack channel.
Yeah, I've got a question over bytes.
Oh, okay. Yeah. Later. Go ahead.
If you use multiple bytes, can you get numbers beyond 120 and 127?
Well, at that point, you'd use a short. You would just you would use a larger value type to get larger values.
Well, I know it's a thing in some video games to use multiple bytes to store big numbers.
Well, I think the common thing that you would see in a language like C and C++ is you could actually create variables of type like long, or byte, I think is maybe what you're talking about. So technically you could accomplish that, but 2 bytes is 16 bits, which is the same thing as a short. So we already have a name for that, is I guess what I'm saying. And more modern languages that you're primarily going to be working with, like Java and C#, they don't have the ability to stack like that. They force you over to object types if you want to store even larger values. Yeah, so realistically in modern programming, the only time you would actually ever use a byte is probably if you're writing some sort of could be a video game, something with a network communication where you have an online presence or you're doing video streaming, something like that, because those things typically stream in the format of bytes. So this is just the right size bucket to catch one byte at a time as it's coming in. Make some sense?
I guess.
Okay, so once we get into seeing how these things are stored, I think it'll make more sense, or at least maybe you'll have a question that you could rephrase the question in something I can answer with an example. But for right now, if the question is, how do I store a number outside of the range of -128 to 127, you use a short. That's the next bucket for holding things that are larger than that. And if the value it doesn't fit inside of this range, then you'd use an int. If it doesn't fit inside of that range, then you'd use a long. If it doesn't fit in that range, then you jump over and use one of the objects that typically comes with our modern languages that allow you to hold arbitrary size values at the cost of speed. Things slow down the larger the number you're trying to hold.
Yeah, maybe I can bring in the example I had in mind someday.
Okay. Or email it to me. I'll take a look at it. Okay. So a float, and this is kind of what I was saying before, similar to C and C++, a char is 8 bits. In Java and C#, a char is 16 bits. All the other things are the same, just the size of it is bigger because Java and C# use Unicode instead of ASCII. Same thing with a float. In an older language, a float is signed. Actually, you know what? I think it's been updated in modern compilers. Doesn't matter, it'll go the same way. So a float is a 32-bit value before the decimal point and a 16-bit value after the decimal point. So that means before and this after the decimal point will be unsigned because you would never have like a negative number on the decimal point side of things. So this can hold negative numbers in the range of -2.1 billion to +2.1 billion on the left side of the decimal point, and it can hold values between 0 and 65,535 on the right side of the decimal point. Whereas a double is 64 bits before the decimal point and 32 bits after the decimal point. And realistically, you can think of this like an int. This is like the decimal point value of an int. So whereas this guy is more like a long. So the same problem solving that went in with those two ideas, an int versus a long. An int can hold a 32-bit number, a long can hold a 64-bit number. Float and double are kind of the same kind of animals, but for holding decimal point values. All right. Lastly, Booleans, trues and falses, and we'll see all these through examples. All right, so what we want to get from this slide, and I'll never ask you to like tell me the range of values for these, but I want you to appreciate where these things came from because these are connecting it back to what we've been talking about for 2 weeks, right? All these things with bits and bytes and binary stuff, yada, yada, yada. All right, so when you first open the package with C, C++, Java, C#, these are the things that come with it. All right. Now I mentioned on this slide, the syntax for our variables is the variable type, followed by some name, and then optionally you can set it equal to a value. So let's go and write some of this stuff. So I have a link for this already on Blackboard. If you have a different tool that you prefer to use, I'm fine with that. But we have a tool called Online GDB. Just log in here. I don't want to enable it. Oh my God. All right, we're not doing that. Let's log in with. Okay. So when you go to online GDB and you log in, create an account, doesn't cost you anything. This is a pretty cool tool that I'm going to do all our work in here in, but nothing says you can't use your own C++ compiler if you have another tool that you like, or you like using Microsoft Visual Studio or whatever it is. There's a zillion different C++ compilers out there, but I don't want to have to play tech support for 50 different people installing all sorts of different software on their computer to learn beginning programming. So this website, very good website, onlinegdb.com. Like I said, there's a link on Blackboard. What's cool about this is when you first go here and you create a new project, up in the upper right-hand corner, there's a drop down. Here's all the languages this guy supports. So you can code in any one of these languages inside this window. Now notice there's 20 different versions of C++ as it's been updated over the years. So we have our oldest language, C, then kind of your first iteration of C++, and then these guys are updates over the years. And this is 2014, 2017, 2020, 2023. Turbo C is older, and Turbo C++ is older. So these are probably the first two that came after this guy. And here we're just going to be using C and C++. Just the standard things. All right. As I mentioned a little bit ago, though, I'm going to use the C++ IO pieces. This is actually a C program, what we see right here, because it's using printf to display stuff to the screen. You're going to see as soon as I choose C++ here, it switches it over to something called cout for writing stuff to the screen. But you would have noticed not much else changed. Okay. All right. So let's kind of go through this. Usually when you first start programming, the first thing you do is you write a hello world program. Something that just displays hello world to the screen. All right. So it gives you a hello world program initially. You can hit run up here, and there's your program running down here. Hello world. All right. So let's talk about some of these pieces in here. One thing that's not being shown here that would have existed in the early days of C and C++ is something called something that looked like that. So one thing we're going to say is all programs begin and end with main. Let's get that in the slides. Main function / method. All programs begin and end with main. So that means when you first run your program, when you hit play, or if you're using a different tool, an older tool where you compile it and then execute it, what it's going to do is it's going to jump to line 1 of main, because the program begins at main. And it's going to keep walking down this guy one line at a time until it hits the end of main. Now, in the middle there might be calls to some other functions or something where it transports itself to some other part of the program, does some stuff there for a while, but when all is said and done, it's going to make its way back to here and keep going down the line. All right. So all programs begin with line 1 of main and end with the last line. All right. That's what these curly braces are from. And we'll talk more about this as we kind of get further into it. All right. Next thing. Why does main have a value that says int in front of this? So main is actually a function. This is the return type for the function. This is the name of the function. This is the parameters. And we'll talk about functions soon enough, so you don't have to get into the weeds of that. Just that's what we're looking at here. But the question is why might the main function return an int? Modern languages like Java and C# have main returning void, which is nothing. The reason is This language is old. Back in when C and C++ first came out, we didn't have graphical user interfaces. The way you launched a computer program wasn't double clicking on some icon. It was either calling your program from another program or typing it at a command prompt. And you might be interested if everything worked out okay. Because when the program runs, your modern programs, if something goes wrong, you get a little pop-up window, right? That says, something went wrong. Press OK to continue, right? Well, that doesn't exist in non-graphical applications from a long time ago. Well, so that means if you wanted to have a way of knowing, did everything go okay, or a way of giving error codes coming out of it, what would end up happening is at the end of main, you would return a value. So 0 means everything went fine. All right. Now, the reality is you can choose to say void there and choose not to return anything, and it'll still work. Oh, it must be int because we're using not the newer version of C++. So really, that's a lie. Okay. So we'll put this back to an int. All right. So that's what that piece is for. It's for old time error codes. Not that you'll never run into that today, but you'll rarely deal with that today, because usually when you're working professionally today, you're going to be working with more modern operating systems and you'll have new ways of handling errors. Secondarily, again, along those same lines of these older programs would have run from a command line, not from double clicking or something like that. So it would not. So for example, if we are running on a Unix terminal, so here is a okay, so here is a Unix terminal. So for example, there's a program called ls that I just ran. And ls doesn't require any special things after it. But let's assume that I want to edit this setup.py. This is a Python file. So there's another program that's on this machine called VI. It's a text editor. And in order for me to use this, I actually have to tell it what file I want to open. So I would say I'm going to open setup.py. So in this case, I am calling a program called VI, and I am passing it a command line argument, giving it some information. And if I do that, it'll open up a text editor here with all that stuff in it. All right. But thing to focus on here is this is the name of a program, and sometimes programs might need you to pass something to them when you first launch them, a command line argument. That's what this junk is for. Okay. Now, if you noticed, I added that back in because modern programs typically don't use command line arguments. Not that they can't, but typically when you're running a modern program, what are you doing? Double clicking on something. You don't have that opportunity to type in a command line argument. There is ways to getting them in there. You have to go into like the settings for how to run the program, and you can add in some command line arguments, but those aren't all that friendly to use, let's say. All right, but let's just explain this for a minute. We'll swing back to this at some later point in time, but just to hit the kind of the highlights as we go through here. There are two different pieces of information here for our command line arguments. If we were writing this in Java, this would be public static void main string array arg, something like that. If we were writing this in C#, they use lowercase s for strings. Otherwise, the line of code is identical. All right. Oh, actually, I think they also use a capital M. So in any case, this is Java, this is C#, this is C and C++, let's say. They all are accomplishing the same things. The piece of this to look at that's different, though, is in these new languages, notice that this guy only takes in one input. where this guy actually takes in 2. And that comes down to a limitation in an older language like C and C++. And we'll fully explore this limitation. We're going to be getting into the details of it. So don't worry about it too much right now, just hitting the highlight reel. In C and C++, when we store collections of things, they're called arrays. Arrays do not know how big they are in older languages. More modern languages like Java and C#, an array can report to you how many elements are in it. So in this case, in C and C++, we have to pass in an argument count as well as the argument values. That's what the 2 pieces there are. Where in these newer languages, you just have to give it the argument values because it can tell you its count itself. All right, so we'll just move past that. Again, I'm not going to be testing you on that stuff. Just when you look at C and C++ code, if you start seeing stuff like this and stuff sandwiched in there, that's what it's for. It's for handling command line arguments, which is probably not going to be overly common for a modern programmer. All right, so we'll go back to this version of it. We see we still have hello world working. So this is usually my starting point whenever I start any program. All right, whether I'm using this tool or I'm using some other tool, I quickly write like a simple hello world program and run it to make sure that I have a functioning development environment. Okay. Now, this is a little bit of a funky syntax right here. Cout is how we write stuff to the screen. So let's look at cout function. This is write stuff to screen in C++. C would use something called printf. Java would use system.out.println. C# would use console.writeLine. Might be a capital L in line. But they basically all print something to the screen. All right. Now, it just so happens that cout lives inside of the std, what's called namespace. That's what this guy is. Standard, followed by 2 colons, followed by cout. Now, you might imagine this might get pretty annoying pretty quickly if you're having to write that stupid syntax over and over and over again. If I take out this stuff and I hit run, it's going to yell at me. It's saying cout was not declared in this scope. Did you mean this other thing? You can fix it by saying using namespace std. Oh, sorry. Both of them are equivalent. The difference is when I say using namespace std here, when it compiles and when it links, it's going to pull in the entire std namespace into my executable, as opposed to just enough of it to use cout. But the idea is we have plenty of memory in our modern computers. Who cares? And I'd rather just say cout than std : cout 50 times as I'm writing things out to the screen. Choose your poison because it's doing the identical thing. All right. So cout's the function that we use to write stuff out to the screen. All right, let's look at some variables now. We saw in our syntax here, syntax for a variable is the type, followed by the var name equals value. So let's create an integer. Int age is equal to 5. And then a semicolon. And I can do cout age. And we got 5. Now I'm going to go ahead and say see out hello world again after that. And you're going to see a behavior here that you probably are not going to be thrilled with. When I run that, we see that we have the 5 with hello world right after it. When we have our output for our program, we might want things to kind of kick down a line, that kind of stuff, just so it visually formats a little bit better. Okay, we have 2 ways of handling this. Notice the syntax for see out uses these arrow thingies. All right, it creates a stream. So I can say see out age, and then I can do something like that. And I can put in that character. That is \n, which is line feed, carriage return line feed. Typically \r is carriage return, \n is line feed. Modern operating systems treat it as the same thing. So now if I run this, it'll print out the age. Then it basically hits return. And then it prints out hello world, but I didn't hit return here. Similarly, there's a built-in thing that probably just holds the character \n called endl for end line that you can use that also kicks it down. Choose your poison. All right. Ultimately, this is for your ability to read it. All right. So now we know how to display something to the screen, and we know how to kick it down the line if we're interested. Make sense? All right. So we have an age. Let's create some more variables here. Let's create a double pi is equal to 3.14159, something like that. Interesting thing about modern programming, I mentioned that typically if you're going to hold whole side numbers, the default ninja move is typically an int. That's just naming convention. That's what modern programmers tend to do because we don't care about memory. What's funny is on the floating point side of things, float is kind of the equivalent of int. Yet the default typically on floating point values is double, higher precision. So we actually use on the double side of things, $96 bits of value to hold all of our floating point numbers. But who cares? We got 16 gigabytes of RAM or 32 gigabytes of RAM or whatever. Now we're not going to lose sleep over it. All right. But in the back of our head, we want to know where we came from. And that if you're doing some crazy scientific researchy type thing, you might run back into a problem where storing too much data in memory, you do run out of memory. Very modern example of this is with things like ChatGPT or large language models. They require a ridiculous amount of memory. If any of you have ever tried to go and use one of those yourself, like run your own, Meta, Facebook people, they have one called Lambda. And if you go to download it, they have like 4 or 5 different versions of it, depending on how much RAM your machine has. And the capabilities are different, but pretty quickly you don't have enough RAM to run it. I think their biggest model requires 128 gigs of RAM. All right. So we have a couple of variables here. We have age, we have pi. I can print out age. I can also put a space in there if I want, and then tack on to it the value for pi. So basically, I'm going to say age, followed by a space, followed by pi, and then kick it down a line. So there's that guy. Here's age, followed by a space, followed by pi, and then print it out hello world after that. All right. We could also change the value of age. We could say age is equal to 7. And when I run this, age will now be 7. Because remember, all programs begin and end with main. We start off at line 1 of main. We say we want to create a variable called age of type int, because it's a strongly typed language, so we have to say that. It's going to start off with the value 5. Then I'm going to create another variable. I want to remember another value. I'm going to call it pi. It's going to be of type double, and it's going to start off as 3.14159. But then I'm going to modify the value of age. It's a variable, so I'm going to vary its value. All right, so I'm going to overwrite that 5 with a 7. So by the time I get to this line right here, and I go to print out age, it's going to do what's called resolve that variable. I'm saying I want to print something out. I want to print out something that I've remembered. I've called that guy age. The computer's going to go and look that up for you. It's going to find out what the current value of age is. And what's the current value of age when I got to this line of code? It's a 7. Even though it started off as a 5, I've changed it to a 7. Make sense? All right. So we'll say cout age. It'll print out a 7. We did not change pi, so that's still going to be the 3.14159. So there's my 7. There's my 3.14159.
Where's the 5?
Well, you mean this version of 5 or when I printed it out? Here's the 5 right here on line 7.
Yeah, why isn't it printed out?
Well, because when I printed it out, I printed out age and I changed the value of age right here. So the 5 is gone. I overwrote it. 5 was still alive here. It was still alive here, but as soon as this line was done, I changed the value of this guy to a 7. So the 5 was gone. So I actually never used the 5. And that's why we get a 7 down here. All right, we also have some math operators. So we could do something like int sum is equal to age plus 5, let's say. And then I could do something like cout sum. So I'm remembering another value of type int. The value of that guy is going to be whatever age currently is. Age is currently a 7. Let's stop seeing this ad. Not interested in that ad. I tried to make the text bigger. There might be another way to make it bigger, but whatever. We'll mess with that next time. So I'm going to set sum equal to whatever age currently is, which is a 7, plus 5, which is 12. So 12 is going to get stored in sum. So we're going to see a 12 from that line. So there's the 7, there's the 3.14, and then there's the 12. Make some sense? All right. The last little thing I'll show you ahead of the homework assignment, I'll put the homework assignment up. It's going to have you kind of doing things like this, manipulating variables, that kind of stuff. Is if I do something like int val is equal to pi divided by 2. And then I print out the value of val. Notice I get a 1. What is pi? Pi is 3.14. What's 3.14 divided by 2? Is it exactly 1? No, there's some floating point stuff in there, right? But I'm storing it in a bucket that's only capable, storing it in a bucket that's only capable of holding an int. Doesn't know how to hold floating point values. So what does it do? It truncates. Doesn't round. It just cuts the decimal point on over off, leaving me with a 1. That's why I got a 1 there. Make sense? If you want to do floating point math, I could change that to a double. And now I get the 1.57079. Because I've now put it into a thing capable of holding a floating point value. All right. Questions, comments, concerns, bribes? Good. You only should. You only can define the type once. So what he just asked is, do you only have to define the type once? It's actually a common mistake. So good question. Once you bring a variable into existence, like I did right here, from that point forward, age has already been defined. Every time I want to use it, I do not use the word int again. I just use age. It's already been flagged as int forever and ever and ever within this scope. We'll talk about scope next class. All right, so I'll put the assignment up here in a little bit. Should take you roughly an hour, but there might be some experimentation you have to do. You run into errors, whatever, but it'll get you used to using this tool. All right. I will see everybody on Tuesday.
So no homework?
No, there will be homework. I'm going to put the homework up here in a few minutes. So be up on Blackboard. They'll be due on Tuesday.
All right.
The mark is there for the, and I was trying to figure out what those marks were in between age and pi.
Yeah, it's these guys right here.
Yeah. Okay.
Yep. So it's the
I want to
shift.
flex my code.
So why were
That
they?
was your head. Yeah, it's clapping about.
You don't remember exactly.
Oh, a second. Let me stop the recording.